Rocket launch could become the new way to add data center capacity, not by launching a building, but by launching the next unit of compute. A normal data center expands by filling another building with racks. SpaceX's little stranger idea is to expand by filling a rocket with satellites. The important story here is not just that computers can operate in space. It is the flywheel. AI demand creates demand for compute satellites. Those satellites create recurring launch demand. Higher launch utilization can make reusable rockets cheaper per kilogram. And cheaper launch makes bigger orbital compute systems even more plausible. If that loop spins, launch cadence becomes compute cadence. Every satellite is a rack. Every refresh is another payload. And the company that controls the rocket, the satellite factory, the network, and the demand has a very different type of advantage. So first, do not just picture a warehouse in orbit. Picture a network of satellite nodes. Each node carries chips, solar panels, radiators, laser links, storage, propulsion, shielding, software, and a disposal plan. SpaceX has an FCC application accepted for filing with a proposed orbital data center system of up to 1 million non-geostationary satellites. StarCloud has a public notice for up to 88,000 satellites. These are proposed systems, not approved fleets or constellations, but they reveal the unit economics the industry is imagining. Compute capacity would not arrive as one giant hub. It would arrive as an expanding network. More nodes, more links, more power, more replacement cycles. That is why the question changes from, can a chip survive in space, to can launched hardware become a repeatable unit of compute capacity? Now, why would anybody try this? The demand pressure is coming from Earth. AI data centers need electricity, land, cooling, grid interconnection, permitting, and time. The IEA projects global data center electricity consumption roughly doubling by 2030 in its base case, and the revised research flags the boring but decisive point. Grid capacity can take years to build. Space offers a seductive alternative because solar energy is abundant overhead and certain orbits can see the sun for long stretches. But the orbit does not remove infrastructure. It changes the infrastructure. You still have to launch the solar area, the radiators, move all the data through the optical links, withstand radiation, win regulatory approval, and refresh your hardware when the chips age out. Space is not a shortcut around physics. It is a categorically different type of supply chain. Let's talk about the central theme of this video, the flywheel. So step 1, AI demand grows faster than terrestrial capacity can comfortably absorb. Step 2, an orbital compute company converts that demand into satellite orders. Step 3, those repeatable satellites fill rockets not once, but again and again as capacity grows. Satellites fail, and AI chips become obsolete. Step 4, if reusable rockets fly more often, the fixed costs and vehicle costs are spread across more missions. Operations improve through repetition, and the launch learning curve can push dollars per kilogram down. Step 5, lower launch costs makes heavier power systems, bigger radiators, better optical terminals, and more shielding affordable. That makes more workloads plausible in orbit, which creates more demand and starts the whole flywheel over again. Visually, this is a flywheel, but it's also an S-curve. Early launches are expensive and awkward. Then, if utilization and reuse compound, the cost curve begins to bend, and network expansion accelerates. This is where SpaceX is uniquely positioned. StarCloud can build orbital compute satellites, Google can design TPUs, and may even someday buy capacity. NVIDIA can supply accelerators, and other launch companies may own individual pieces of the stack. However, SpaceX is the one with the clearest path to owning all 4 layers at once. Starship for launch, satellite manufacturing for the hardware, Starlink-style lasers for the network fabric, and possible internal AI demand through the Musk ecosystem. That doesn't make the plan proven. It means recurring payload demand helps SpaceX more than it helps a non-integrated player. SpaceX can be both the builder of the road and one of the first heavy users of that said road. So quick pause. If industrial system level takes on space interest you, subscribe to Galaxial Frontiers and drop a like on this video. We're tracking the places where rockets stop being just a spectacle and start becoming infrastructure. Now let's return to reality a little bit. The timeline is still early. In November 2025, StarCloud said that StarCloud 1 launched with an NVIDIA H100 in orbit and ran a version of Gemini and trained a small model. StarCloud is a separate startup distinct from SpaceX, which makes it interesting. It could compete in orbital compute, but it also buys from the SpaceX infrastructure layer. In May 2026, StarCloud announced a contract for more than 50 Starlink mini laser terminals across more than 25 satellites. In June 2026, public SpaceX discussion around the AI-1 described a satellite concept around 150 kilowatts peak power and roughly 120 kilowatts average compute, using Starlink-derived solar and laser-link technology. Google and Planet are targeting 2 Project Suncatcher prototype satellites by early 2027 to test TPUs and high bandwidth crosslinks. This is a useful sequence: prototype, link contract, regulatory filing, factory ambition, paired test mission. This isn't a commercial scale proof yet. It's the first outline of a market trying to become real. Now let's talk about where the flywheel can break. The first is cadence. FAA's Boca Chica review authorized up to 25 annual Starship and Super Heavy orbital launches at the site, which is a reality check against the much bigger company ambitions. Second is cost. Google's research models low Earth orbit launch below roughly $200 per kilogram by the mid-2030s, and that's under sustained learning assumptions. While JLL points to a $500 per kilogram threshold in some scenarios. Those aren't today's prices. They are the curve the flywheel needs. The third is regulation. FCC filings begin review, but they don't equate to approval. And million satellite systems raise debris, spectrum, astronomy, reentry, and traffic management questions. The fourth is refresh. AI chips move fast. Obsolete satellites either need to deorbit, shift into lower complexity work or use cases, or they become a liability. The fifth is workload fit. The first wins are probably orbital edge processing, secure storage, batch inference, backup, and jobs where the data already started in space. Cooling and networking matter too, but they are supporting constraints here, not the main story today. The main question is whether the loop keeps accelerating or stalls at one or more of these gates. What do you think of the pros and cons of this emerging technology? Hopefully it's clear that orbital AI is not mainly a sci-fi claim, that data centers all move into orbit. It is an industrial bet that compute demand can fill rockets, rocket reuse can lower launch costs can expand orbital compute, and expanded orbital compute can still create even more demand. If it works, a launch becomes an installation event for new AI capacity. But if it fails, it probably fails for ordinary infrastructure reasons: cadence, cost, regulation, customer demand, chip refresh, or just the economics of operating a network in orbit. The next data center customer may not be a company looking for floor space. It may be a rocket waiting for another stack of compute satellites. Thanks for watching this Galaxial Frontiers production, and I will see you in the next video.